This is the optical fiber question. The way a fiber works is it's some sort of glass fiber down the center in the core, and then there's a cladding with a lower index, and we know that's what it takes for a total internal reflection to happen, is you have to be in a high index and have a lower index here. So for light rays that are a very steep angle, they hit the wall and have total internal reflection, so you don't lose any light. It all stays in the fiber. That's how fiber optics work. We know in terms of physics that the angle you care about is the angle of incidence. And when that angle of incidence is at some critical value and bigger, you'll start to have total internal reflection. If it's at a small angle of incidence, the light will go out. So let's see what we were asked. We were asked, what is the minimum angle to stay in? So again, it makes sense that's a minimum. If this is the critical angle, you get total internal reflection, and if it's bigger, you still get total internal reflection. If you go smaller, you don't. That's why it's a minimum. There's a lot of confusion about when we say minimum or biggest or smallest. Really, for these problems, it's always the answer. It's just the critical angle. You actually don't usually need to understand, is it a minimum? How does that work? So it's critical angle. Critical angle formula, I hate to just do formulas, but I don't want to derive it. We derived it in class. Is, it's the case where you have the refracted ray at 90 degrees. So, well, let's just derive it. Why not? We're going to do Snell's law here and say we want the critical case where the refracted ray has nowhere else to go. So it's a 1.53 times the sine of 90 equals 1.58 times the sine of that critical angle, CR minus T. So this is 1. So it's really where the sine of the critical angle equals 1.53 over 1.58. Or you could go ahead and take the inverse sine. It's the inverse sine of 1.53 and 1.58. So there you go. The critical angle is the inverse sine of the ratio of the index outside over the index inside. So that's what it is. And for this one, the answer is 75.5 degrees. So that's a pretty straightforward critical angle optical fiber kind of problem. But for the next part, we can think about what's bad about optical fibers. What's bad is, and of course this could be solved, but whatever, is that some light might go straight down the fiber, and some light might be on this bouncy path. And that means they're going different distances if they go from one end of the fiber to the other. This one just goes the length of the fiber. This one goes some distance that we could calculate with trig. That means if you have these pulses, they're going to arrive at different times at the other end. If you had a really short light pulse, one would arrive before the other. Or the sort of frequency domain information you have here might get screwed up by the time you get over there. Or the timing domain, whatever. So the question, the way this decides to ask the question is for a light ray that goes straight down the middle, that travels 1 meter, how far does the bouncy ray travel? The one bouncing at the angle of incidence. So there's a few ways to do this. You could think about comparing the ray at the critical angle as it traverses the fiber. This is all just the core now. It goes this distance while this straight ray goes that distance. So I'm drawing it at the bottom instead of in the middle because we're just trying to do geometry. And when you're trying to do geometry in these problems, you're always looking for a right triangle. Hey, I see one. There's a right triangle right there. So the actual path that the thing took was, it's going to be 1 meter. This path is going to be longer. So the question is how much longer? Now, of course, this isn't really going to be a meter. So if we know that this is 0.2 millimeters, then this is much shorter than a meter. And this, then we can't really compare them. But you got to realize that when it bounces again, it's the exact same geometry. So if this is a lot less than a meter, well, that same number happens again and again and again and again and again and again and again. So you could solve it that way, or you could just say, I'm going to call this x. It bounces some distance x. Let's just say that. And the straight ray goes x, and the bouncy ray goes h. So we know that that the sine of this angle, the critical angle, is 75.5. We know that's equal to opposite over hypotenuse, right? So x over h, like that. So what we know is that h, we solve this for h and put this over here, and we find that h is 1.033x. Like that. So we know that for every 1 nanometer that you go in x, you go 1.033 nanometers in h. And for every centimeter you go in x, you go 1.033 centimeters in h. For every whatever this actually is, based on the 0.2 millimeters, you go 1.033 times that in h. So if you believe that this same triangle is just happening over and over again, you actually don't need the 0.2 millimeters. You don't need to get this exact distance. You can just call this a meter, because the ratio between these two is going to be 1.033 times a meter. If you believe that whatever happens in this triangle happens again and again and again, and it's just proportional. If you want to, you can use your 75.5. You can solve for x. You can solve for h. You can say how many x's does it take to make a meter? Do that many h's. It's the same thing. But you can see that if x were 1 meter, then h is going to be 1.033 meters. So the problem asks how much farther in centimeters, so the difference between 1 and 1.033, 0.033 meters, 3.3 centimeters. The delta is 3.3 centimeters. So just a 1 meter fiber, one went a lot farther than the other by 3.3 centimeters. So this is an issue you have to deal with in optical fibers.